All right, welcome everyone to the award ceremony session. My name is Babak Falsafi and I'm the Cigar chair.
And I'm Joseph Torellas from the University of Illinois. I'm the TCCA chair. In this hour, we will proceed to present the awards. Note that all the awardees, with the exception of the EckertMauchly awardee, have recorded their speeches and they are available at the ISCA website.
The EckertMauchly Award will be live streamed and introduced by Per Stenstrom. And the Q&A will be handled for the EckertMauchly Award will be handled through the platform. There are no Q&As for the awards. Okay, so Per?
Yes, hello everybody. I'm Per Stenstrom from Chalmers University of Technology. As you know, the EckertMauchly Award is the most prestigious award presented to an individual in the computer architecture community. And it is often referred to as the Nobel Prize in Computer Architecture. Specifically, it recognizes outstanding contributions to computer and digital system architectures where the field of computer architecture is considered encompass the combined hardware-software design and analysis of computing and digital systems. So this year, the selection committee consisted of myself, I was chairman, and Natalie Enright-Jurger of University of Toronto, Kim Hazelwood of Facebook, David Cayley of Northeastern University, Li Xuan Pe of Natural University of Singapore, and Andrei Sesnek of IRISA INRIA. Next. It is a great honor for me to introduce the 2021 winner of the ACM IEEE Computer Society EckertMauchly Award. This year's winner is Professor Margaret Martonosi of Princeton University. Margaret has made many contributions, but the citation reads, for contributions to the design, modeling, and verification of power-efficient computer architecture. It is my great honor now to give the floor or the screen to Professor Martonosi. Thanks.
You're muted, Margaret.
Welcome to 2021. I'm muted. Thank you. So thanks very much, Per. Thanks to everyone for this honor. And it's a real joy, and I'm very grateful. So when I thought about how to approach this talk, I thought a bit about Eckert and Mauchly and ENIAC. And at one level, we know them as hardware guys. But the thing is, ENIAC was very much a full stack project. It got its fame. We know about it today from the fact that it was not just electronics, but also programmable. And so I want to note here the names and contributions of 6 additional people, all women, who programmed ENIAC and thereby contributed to the project's life, soul, and impact. So I thought I would start with a bit of a roadmap of my research timeline. And right now we're pretty close to the 35th anniversary of me fairly spectacularly failing my PhD qualifier exams. And so you can consider this to be a road to redemption of sorts. I'll give the high-level view here, and then I'll dig in more detail. And one of the themes that I hope you'll see throughout all of this is the value of full stack research. So if you start over here, in the early days, I was working on parallelism and also aspects of FPGA specialization. And to get from sort of here to power awareness, I clearly remember the conversation with David Brooks, my then PhD student, where he noted and we agreed that we'd been talking about bit-width optimizations for FPGA designs, for FPGA specialization, but some of the best uses of bit-width tailoring seem to actually be for power and general purpose processors. A fork in the road a little bit later, in the early 2000s, was a project then to look at zebra tracking. And while some, including sometimes me, thought it might be a midlife crisis of sorts, it was exciting to be able to see the unexpected linkages between power efficient systems and zebras. About 5 years later, I started co-advising Eric Chi with my colleague Steve Lyon as an early entry into quantum computing architecture for me. And I won't have time to talk much about QC, but that was a fun path on its own. And then most recently, my then PhD student, Dan Lustig, encouraged me to try seeing how formal verification research would work in an architectural context. And so that sort of brings me out to this far end. So over all of this, I would note that when you're bringing somewhat new topics to the community, like these were, it's been important to remember that these weren't obvious ideas for our community. And the first paper submissions weren't perfect publications when we first put them out there. So when the community moves into an unexplored area, we don't get a roadmap. There were doubts from us and from reviewers. But I'm really glad that we were able to move forward despite those doubts, because each of these pivots has represented new territory and new opportunities for architects. So we're going to start back here with power efficient systems and take it from there. So my work on power efficient systems began with this narrow bit width paper that I alluded to earlier. It was about saving ALU and register power by recognizing when the calculations were on numbers smaller than the full machine bit width. And then that paper in turn motivated the Watch power modeling paper because we recognized that working on power aware optimizations would be helped by having early stage estimators to quantify potential benefit. So the ISCA paper on Watch is my highest cited paper, and it's often what David and Vivek and I are known for. And I'll say here also that it's probably the lowest review score accepted paper I've ever had. The reviewers found quite a few things wrong with that paper. But fortunately, they also saw the promise and they accepted it for what it got right. Namely, that it articulated the role of architects in thinking about power much earlier in the design process than had been common at the time. And it demonstrated that usefully accurate power models could be a part of the architect's toolbox. I'm proud that that paper, along with some others, managed to encourage the field of architecture in a bold new direction and also give them the beginnings of some tools and techniques with which to go there. So Watch wasn't the last word in architecture level power analysis by any means, but it didn't need to be. It was one of several papers at the time that anticipated a need and got the community starting to fill it. We spent the next several years building out our ideas of power awareness up and down the stack. Cache decay for leakage management in caches, power and thermal estimations based on live performance counters, and then using those sorts of things to drive other system adaptations through phase analysis and other control techniques. This was being done at an exciting time when many in the field were starting to dig in on different aspects of power and thermal challenges. And it's invariably hard to start naming names. So this list will certainly be incomplete, but some of the ones that spring to mind from that time were Janie Irwin, Vijay Narayanan, Bobby Manet, Iris Bohar, Joel Emmer, Trevor Mudge, Kevin Scadron, Pradeep Bose, and on and on and on. So this layer cake is just my papers. The full community's work would be much larger, obviously. And even so, this is just some highlights of papers, not the full list. And even so, when you step back, the purpose isn't the papers per se, but the way they lead to impact. And so when I think about impact here, I think one form of impact came from the fact that we were willing to work up and down the stack like this, to reach up, to do a lot of full stack real system measurement based on performance counters and thermal sensors and other direct measurements. Another form of impact came through working with industry, licensing technology where appropriate. We collaborated with companies, and I did a sabbatical at IBM. And obviously, a lot of students did internships as well. So right around the time the Watch paper was published at ISCA'21, I got tenure. And this is the headline from the university staff bulletin. Check out my really fancy monitor there. When I got tenure, I sat down and I wrote a paper list of what was next. And I still have that piece of paper. I keep it with me. There were a lot of good ideas there. I wanted to do more group-oriented research with multiple students and faculty working together. And I wanted to do more real systems prototypes and deployments and so on. So right around the time that list got written, I got an email from a colleague. And all it said was, remind me to tell you about zebras. That became, in time, a collaboration with biology professor and zebra expert Dan Rubenstein, who you can see here in the lower right. About power efficient devices for zebra tracking. So today, you could use a ruggedized cell phone with solar recharge for location tracking. But back then, smartphones didn't exist yet, GPS barely existed, and rural Kenya had no cell service. So the biologists were literally doing some of the things that you see in these photos here. But in addition to all of that, there were also serious energy constraints and system reliability challenges for long-term deployments. And it was that tie that drove us. So while it at times might have looked early on like some sort of Margaret midlife crisis, the zebra tracking work, the power constraints that it demonstrated intertwined really well with the power-aware architecture group that other parts of my group were also doing. By the end of our project, we demonstrated multiple generations of real working systems with hardware and protocols and collars that we designed and built. So we built the collar that you can see the zebra wearing, and on a previous generation of collar, I personally sewed solar cells onto them. This offered huge energy savings and huge improvements in wildlife data collection over hundreds of square miles in Africa. And the data would help biologists understand why certain zebra subspecies were endangered while others were not. Back to architecture, this work helped inform a lot of our thinking about notions of architectural balance in energy constrained systems. For example, why were so many sensor network researchers at the time relying on 8-bit processors? Think about it, 8-bit processors, when they were such a small part of the overall power budget compared to the radio and so forth. To us, it made sense to use a 32-bit processor and be able to run something fairly close to a real operating system. And our deployments help demonstrate this. So we did 2 deployments on zebras in Kenya. We did 5 generations of the electronics, one of which you can see in the upper right, and we did 3 generations of the collars. Like our other work, ZebraNet was a full stack project, and it had a layer cake of results also. We demonstrated the energy savings of application-tailored on-sensor computation in order to downsize the data that needed to be communicated elsewhere. We developed different localization approaches that reduced power by reducing how often we used GPS. Does this sound familiar? So these trade-offs of trying to put data near compute, trying to compute near where the data is and avoid communication energy are things that remain important for our field today. So back to the timeline. We're now out at the far right. My work on verification is newer and it isn't over yet, but it has some of the similar story elements. So the goal in this work is to use formal techniques to check whether a given implementation abides by an axiomatic specification of its concurrency rules. And like my group's work on power 20 years ago, our work on memory consistency verification is rooted in the belief that architects have a strong role to play in early stage verification, much like our watch tool and other early power work established the architect's role in early stage power analysis. For a long time, a lot of verification was viewed as being the role of circuits folks and late stage design and fab tools. And we were trying to shift it earlier. Another similarity is listening when smart PhD students have good ideas. And in this case, Dan Lustig brought us into this verification space at a time when I had some doubts. And with that, he and I and others, including Caroline Triple and Yatin Manerkar, began a sequence of work that continues to this day. So like the power topic, our goal was to say, hey, architects should be helping with this. And also like the power topic, we felt it was important to not just say that as a slogan, but also to bring tools, to be a provider of tools that could help the community do it. And also like the previous topics, we started at one point in the stack, that goal of verifying microarchitecture against architecture, and then we built up and down the stack to better encompass the full hardware software space. So from that initial goal of verifying pipelines against an ISA consistency spec, this work has had an impact in a range of scenarios, including influencing the design of the RISC-V instruction set, and also demonstrating ways that security vulnerabilities can be discerned and automatically synthesized through these techniques. And in the process, we identified new Spectre and Meltdown style variants. So that was a quick whirlwind tour. So let's shift gears and talk about what's next at a higher level, what's next for the field. In terms of what's next for the field, I like to start by looking backwards first. So if you go back to the 40s and 50s to Eckert and Mauchly's time, you have these systems where they had algorithms up high, they had logic elements down low, And they built real systems, so they filled in the middle functionally, but they didn't have any of the clear layering or abstractions that we have now. That came later. And so over time, we built up the hardware software stack that is familiar to us. But a shift is underway, and I think we're all aware of this shift. So embracing heterogeneity is what we have needed to do because of end of Dennard and late Moore's law scaling reasons. In the process of embracing this heterogeneity, we've also added complexity, and we've lost portability, and we've lost programmability. Many of us are working on how best to design modern accelerators, and even more importantly, how to bring back that programmability we've lost. So as part of that, we need to design in the verifiability and the security that honestly we've never fully had, but we need so very much right now. And I hope through all of this, we're going to retain our awareness of our wheelhouse as architects to think about portability and programmability in this space. It's not enough to design a cool, fast accelerator. It needs to be designed in a way that we can program for it and still run that program effectively on a new implementation 5 years from now. And with all this specialized heterogeneous parallelism, there's also both a need for and an opportunity for new methods of formal specifications and the synthesis and verification tools that could build off of them. And then down low, there's technology trends too, and I think there's opportunities there as well. So we, as a field, have a skill set regarding abstractions and hardware-software interfaces, and that can be a crucial ingredient in making sure that new technologies go forward in the most useful way. So whether that's DNA storage, or quantum, or others, the key, I think, is to have architects in the conversation, to be in the room where it happens. So I want to pop up another level for our last few takeaways. First, I think our field will be at its healthiest and most impactful if we view our opportunities without unduly sort of bounding them or delineating them to what is architecture versus PL versus algorithms or whatever. We need to remain open to the possibilities that emerge when we take our architecture way of thinking about abstractions, about hardware software interfaces, and apply that in new ways, and apply it to societal challenges and opportunities. We can't be impactful, or can't be as impactful as we could be, if we all insist on everyone coloring inside lines that are too narrowly constrained. So what does this mean? It means that this openness should infuse how we pick our own research projects for sure, to look for big opportunities and for societal impact. And then we need to shape that into how we review papers, how we advise our students, and how we think about the role and future of our conferences. So how would you envision ISCA 2031 happening in a way that best sort of sets us up for success there? And the second takeaway is about people. So as a community, we've been through a lot in recent years. We've all been impacted by COVID, some more than others. We've navigated challenges around diversity and harassment, and we're becoming a better community, better research community, because we started conversations and we took that on. In addition, 2 years ago at this very conference, we had a student suicide and related ethics concerns in our community that have rocked us to our core, and that we're still trying to learn from and improve ourselves. We need to work more on these issues, and we really need to dig in. I'm proud of and grateful for those who have given of their time and their love and their caring to make us a better place through CARES, through CASA, through WCARC, through all the various ways that we cultivate the ideas and the talent of our future research community. We can always do more and do better, though. I know I can. And I hope we come together as a community to think about what's next. In particular, we should come together to consider how to take on the ethical challenges of our field. We need to tell our university leaders, our corporate leaders, and our professional societies, ACM, IEEE, and others, how they need to change their way of doing business in order to maintain the safety and credibility of ideas and results in our community. And even more so, that they need to change the way they're doing business in order to maintain the safety of people in our community, regardless of their seniority or stature in their career or stature in our community, from students to senior researchers, first-time ISCA attendees, and so forth. I also want to use this slide to say thanks to the whole bunch of people who engage in so much of the service that makes things happen. These are the conference organizers, the officers and boards of Cigar, TCCA. It's also the role models and the mentors. They don't always have official titles, but they're out there, they're helping. And to all of you, I say thank you. And as always, I am imperfect, but I'm always trying to pay it forward based on your inspiration. So this slide is to thank the funding agencies, the companies, and Princeton University who've supported my work for over 25 years. And all I can say is that they have been difference makers at so many key moments. I want to thank my parents. They always stressed the value of education and the opportunities that science offered, and I'm so grateful for their love and support. Next, I want to thank my husband, Kevin Berkman. He's just downstairs zooming himself right now. We met over 25 years ago, soon after I landed at Princeton. We got married soon after tenure, and here we are. I call him my island of sanity. He's been there through the ISCA all-nighters, the travel, the zebras, and so forth. And I'm grateful that he's been my supporter and my best friend through it all. And finally, when I think about my career, the most amazing thing has been the incredible opportunity to meet and work with amazing people. Minus a couple shy exceptions, this photo includes my graduated PhD students, my current PhD students, my current and former postdocs, and others who have co-advised students with me and generally added so much to this amazing experience. So this slide is dedicated to you. You've done so much. You have led me on some incredible intellectual expeditions, a few of which I've gotten to talk about today, and many of which there wasn't time for. We talked through ideas, we puzzled through data together, and we worked together to anneal words into paragraphs, into published work that others could build on. Along the way, you also taught me some great cake recipes. You ran turkey trot 5Ks with me the morning after the ISCA deadline. You welcomed me to visit your families, and you even got me to restart jump roping at the ripe old age of 56. So if we were somewhere in person, I'd ask you to stand and share in this recognition, because this award is as much yours as it is mine. Thank you from the bottom of my heart. And with that, thank you very much, and I'd be happy to take questions.
Thank you very much, Margaret, for a very interesting talk. So I'd like to open up for questions. There is a comment. I truly love the takeaways presented by Margaret. Congratulations on a well-deserved award. Are there any questions out there?
So I first met Per at Stanford University, where there was no shyness about questions when I was a grad student there and he was a visiting scientist. So Per, you can feel free to barrage me with questions. Absolutely. To bring back some of those memories if you'd like.
Yes. Yeah, so while we're waiting for more questions, let me ask you a question. So it was very interesting how you actually started new directions during your career. But you didn't mention how you ended up on your more recent topic, quantum computing. Could you comment on that?
Sure, that's a fun story. So my colleague, Steve Lyon, we were both at that time in Princeton's electrical engineering department. He was more from the device physics end of things. But we had one coffee machine in the department. And so we were standing by the coffee machine waiting for it to brew. And he started telling me about some ideas that he had for a new kind of qubit. And Steve worked on the ZebraNet project with us, for example. He's always been very good at sort of reaching up across different disciplinary layers. And he explained the qubits in a way that we could both see architectural opportunities about balancing compute latency against parallelism. That was the early ideas were about, like, maybe we could overcome long compute latencies by being more parallel in our qubits. It was very early on. I think that paper was kind of blew my mind. That paper was 2006. So, you know, it sort of overlapped with some of the ZebraNet and power-aware stuff. Mm-hmm. And yet so it was idealized in terms of the qubit counts and so forth, but it had this interesting idea of architecting for a particular technology. And it did get born while waiting for coffee to brew.
Interesting. Meanwhile, we got some questions, in fact. So here is one. Margaret, congratulations on this well-deserved award. My question is, do you have time for anything else?
I love this, and I love working with my students. And these days it's a little busy because I do have another job too. But it's always been a joy. It's a bit of a juggle, but I do have time for other things. I was just emailing with a colleague today about a hiking trip 2 years ago in Switzerland, and I was reminiscing about that and so on and so forth. So hiking, swimming, yes.
Great. Another one here. Thank you for a great talk. What was your most memorable review?
Not so much a review, but I will say that I was on the program committee when the watch paper was submitted, and I didn't have tenure yet. And so I remember sitting in the room all day pondering, knowing that this was about as good work as I could do, and thinking that if this didn't get in, I was going to go become a long haul trucker or something else, right? So I probably wouldn't have taken such dire action, but I do now tell my students, when you get a review, you should step away, and you should not make any career decisions based on the review. And in the end, they accepted the paper, so happy ending.
Yeah, that's a good advice, really. What would be your advice to young undergraduate computer architecture enthusiasts?
I think my advice is in my takeaways, that I think we bring this extraordinary way of thinking about how to reach up and down the stack, right? We are where application trends meet technology trends. And as Hennessy and Patterson said in their Turing talk, there's so much excitement that comes from being at that meeting point. And so I would just try to get into different research opportunities where you can. And play the long game, right? People, not every research idea pans out, not everything that you're hoping for pans out, but play the long game and look for the big opportunities, and don't worry too much about whether it's architecture or architecture adjacent, but do what's interesting and compelling.
Thanks. Here's another one. You mainly talked about successes. What about big failures? How do you dealt with failures?
Well, I started the talk by talking about epically failing my PhD quals. And I will say that my first response to failing my PhD quals was to interview for jobs. And I'm very grateful for one of my grad school friends who pulled me aside and said, you know, Margaret, basically, I was interviewing for jobs because I didn't want to fail quals a second time. You could take it a second time, but I didn't want to take it a second time and fail. And he pulled me aside and he said, you got to be in it to win it. So why would you be afraid of failing it the second time? You might as well try and see what happens. So that was that. I could probably think of some more recent. The more recent they are, the harder it is to kind of reflect on them with the right perspective, I think is fair to say.
Right. I think we have time for one more. Congrats, Margaret. You talked about several research directions and inflection points. Any reflections on topics, areas, ideas that didn't work, and why?
So let's see. So, well, here's one. So after ZebraNet, we started looking for other places that we could use that style of delay tolerant networks. And some of them worked, but in other cases, what happened was cell phone service sort of overspread the world much faster than maybe we anticipated. And therefore, the role of these delay tolerant or disruption tolerant networks to connect disconnected regions subsided a little bit. And people weren't willing to use opportunistic dynamic networks when there were very predictable fixed networks with cell phone towers you could always find. And so I think that was a place where, you know, another technology trend came along at a pace that was different than what we expected.
Thanks. I think we need to stop there. Again, congratulations, Margaret, and thank you very much for a very insightful talk. Thanks.
Thank you all. Take care.
So now we move to in memoriam. Janos Sazadis will be presenting this. Jano, unmute.
Hello, everyone. I'd like to say a few words to honor the memory of my dear friend and colleague, Vasos Sotiriou, that passed away at a very young age last September. Vasos was an associate professor at the Cyprus University of Technology, and he graduated from Princeton. He worked with Lishuan there for his PhD and got a BSc from Rice University. He worked in industry and research labs with research contributions mainly in interconnects, NOCs, and multi-core architecture. People that work with him and collaborated, they were working with someone very talented and motivated. He was characterized by his pursuit for technical excellence. He was a great teacher, mentor for his students, colleague and friend. Those of us that were fortunate to meet with him and work with him, he was a great heart, really genuine. And when you met Vasos afterwards, you wouldn't forget him. He was really special. His loss was devastating, and especially given, you know, he had his firstborn last year, a few months before he passed away. So it's a big loss to don't have Vasos away. May your soul rest in peace, my friend. And I'd like to thank ISCA organization for giving us this time to honor Vasos' memory. Thank you.
Thank you very much, Jano. Thank you.
So we now move to, so recently we decided to offer a little recognition to members of our community who retired. This past year, Professor Wenmei, who retired, he received his PhD from UC Berkeley in 1987, and he was a professor from the Electrical and Computer Engineering Department at University of Illinois from 1987 to 2020. He retired in 2020, and but he seems to be doing some site work at an NVIDIA right now. So congratulations, Wenmei.
Yeah. Thank you. Okay, ACM Fellows for 2021. We have 5 fellows this year. David Brooks for contributions to software and hardware design for power efficient computer architectures. Antonio Gonzalez for contributions to the design of energy efficient and resilient computer architectures. Lizzie Corian John for contribution to design, modeling, and benchmarking computer architectures. Nam Song Kim for contribution to design and modeling of power efficient computer architectures. And Scott Mauchly for contributions in compiler code generation for instruction level parallelism and customized microprocessor architectures. So congratulations to all new ACM fellows.
And now we move to the IEEE fellows next. So I'm not going to read all the quotes here. I'm just going to mention the names. We have Rajiv Balasubramanian, Kirk Cameron, Natalie Enright Jerger, Bruce Jacob, Daniel Jimenez, Stefanos Kaxiras, our boss, Jose Martinez, Jose Moreira, Andreas Moschovos, and Xiao Rui 1. Congratulations to all of you.
Thank you. All right, Natalie.
Hello, everyone. I'm going to present the ACM Cigar IEEE CS-TCCA Outstanding Dissertation Award. Next, please. So this award recognizes excellent thesis research by doctoral candidates in the field of computer architecture from the past calendar year. The selection committee consists of myself as the chair, David Albanesi, Antonio Gonzalez, Jayuk, Martha Kim, and Janos Sidaisis. Next, please. It's my great pleasure to recognize this year's dissertation award winner, Dimitris Skarlatos from the University of Illinois, advised by Josep Torellis. He receives this award for contributions to redesigning the abstractions and interfaces that connect hardware and operating systems. Congratulations, Dimitris. Next, please. We also awarded 2 honorable mentions for this award. So the first honorable mention goes to Yatin Manarkar from Princeton University, advised by Margaret Martonosi. And he receives this honorable mention for developing scalable, sound, and all program hardware verification methods that demonstrate the potential of progressive correctness verification from early stage architectural design to late stage implementation. And our second honorable mention goes to Hayuk Jun Kwan from Georgia Tech, co-advised by Tushar Krishna and Michael Palau. He receives this honorable mention for developing mechanisms to quantify the relationship between deep neural network mappings, data reuse, and communication flows for system design of flexible deep learning accelerators. So congratulations to our 3 winners. Thank you.
Thank you, Natalie.
All right, and we now move to the 2021 IEEE Computer Society TCCA Young Computer Architect Award. Next, please. So this award recognizes outstanding research contributions by an individual in the field of computer architecture. It's open to anyone who has completed their PhD degree within the last 6 years. This year's committee was chaired by Tom Venish from Michigan, Per Stenstrom from Chalmers, and Carol Jean Wu from Facebook and University of Arizona. And the winner is, next. The winner is Adrian Sampson, professor at Cornell University. The citation says, for contributions to approximate computing and hardware synthesis from high-level representations. Congratulations, Adrian.
Thank you, Giuseppe. This year's 2021 ACM Cigar's MorrisWilkes Award. The MorrisWilkes Award recognizes outstanding contribution to computer architecture made by an individual whose computer-related professional career, his grad school or full-time employment, whichever began first, started no earlier than January 1st of the year, that is 20 years prior to the year of the award. This year's committee was chaired by John Carter from IBM and included Sandhya Dwarkadas from University of Rochester and Tim Sherwood from University of California, Santa Barbara. This year's award winner is Tom Wenish from University of Michigan and Google for contributions to memory persistency and energy efficient systems. Congratulations, Tom. Izzy? Oh, yeah, there we go.
So 2021 ACM Cigar and IEEE Computer Society TCCA ISCA Influential Award is going to be presented now. Next. This award recognizes the paper from ISCA proceedings 15 years ago. So for this year, it is ISCA 2006. And from ISCA 2006, the paper that has had the most impact on the field in terms of research, development, products, or ideas in the intervening years. The selection process that's used for this award is the ISCA program committee of this year. They vote on candidate papers. So all PC members are invited to vote, select up to 3 papers and or in the first choice, second choice, and third choice. And then those are aggregated by the PC chair. And the final decision is made by the PC chair, myself, and Cigar chair, Babak, and TCCA Chair Joseph Torellas. Next. This year's the 2021 ISCA Influential Paper Award goes to James Donald and Margaret Martonosi for their paper, Techniques for Multi-Core Thermal Management, Classification, and New Exploration. This was in the proceedings of the 2000 ISCA, which was the 33rd ISCA. Congratulations, James. Congratulations, Margaret. Again, the second time today. Congratulations. So happy. Next.
Thank you, Lizzie. This year's ACM Cigar Allen D. Berenbaum Distinguished Service Award was presented by myself and Eileen Locke. Let me just present Alan first. So, well, I as a grad student, I knew Alan from the community. Had great memories, but just a little bit of a service record. He was a sweetheart from our community. He had a distinguished service record within our community, service from 1993 to 2007. He was secretary and treasurer from 93 to 99. He was chair from 99 to 2003. Then he was past chair again from 2003 to 2007. Then he was on the state governing board. He instituted the MorrisWilkes Award for mid-career recognition. He moved the ISCA proceedings to the ACM Digital Library. He instituted the first initiatives in diversity and inclusion in our community with the companion grants for childcare and disability. And he was also the inaugural winner of the Cigar Service Award. So with me here are Eileen Locke, is a partner. Eileen, by the way, was the first general counsel and former chief compliance officer at IEEE. So she's also part of our community. And with us also is Alan's sister, May Berenbaum. So let me just pass this to Eileen first.
Thank you. Alan and I were together from the time we met as graduate students at Princeton in 1973 until January 2016, when he had been diagnosed with the most virulent form of T-cell lymphoma that Memorial Sloan Kettering had ever seen. He passed away 3 weeks later, and I canceled our plans to attend this conference in Seoul, Korea that summer. It's very fitting that Cigar should be honoring Alan for his service to the computer architecture community, but his service to technology was beyond a narrowly defined technical community. He was indeed a Renaissance person who was interested in the arts and the flourishing of civil society in all its forms, which he managed to marry to his technological expertise. A chip design that he had done during his days at Bell Labs was a signature piece at an exhibit at the Museum of Modern Art on technology and art. And in his spare time, he was a computer advisor to the Ensemble for Early Music in New York, helping them move to the digital age. Alan was a great promoter of women colleagues and may have been one of the first scientists at Bell Labs to work very successfully with a female boss. Prior to his passing, after the halcyon days at Bell Labs, Alan was the chief architect at Microchip Technologies, which, as many of you probably know, is the design fabricator for many of the large, well-known computer manufacturers, including a well-known certain company in California. Alan struggled with having one foot in the research community and another in commercial applied sciences. He normalized this by teaching as an adjunct professor at Cooper Union, where he donated his time focusing particularly on helping students whose native language and culture was not grounded in the US. We are known by the company we keep. Alan was an advisor to Lillian Schwartz, the well-known artist in residence at Bell Labs, and as you saw, the primary force behind the MorrisWilkes Award, who was a great friend to both Alan and me. So I want to thank ACM and Cigar for this tribute and hope that the way in which Alan lived his life professionally and personally will serve as an inspiration to computer scientists just starting out to look beyond the development of technical expertise to a world of service in the betterment of quality of life for all of us. Back to you, Margaret.
Thank you very much, Eileen. So this year's the award recognized an individual who has contributed important service to the computer architecture community. The committee was actually chaired by Wenmei Hu. I apologize for a typo there. And also included Lisa Hsu and Matt Ferentz. And this year's award goes to Per Stenström from Chalmers University of Technology for the creation and successful implementation of the Taco High Peak Journal First review model, and for decades of long exemplary service contributions to the field. So congratulations, Per. On that note, this is the end of the award ceremony. We will have all pre-recorded speeches online on the virtual platform, but also all the talks and recordings will move to the YouTube channel, and we'll send in the coming weeks also on the social platforms a little snippet with the collection of all the pre-recorded speeches to remind people of the videos and have everybody have a chance to look at it. So thank you all, and this is the end of the session.
Thank you, everybody, for participating.